So the hole in plane makes sense because it's a hole in my knowledge I found. So I'm going to say some sentences which are not at all my specialty and which I don't really understand very well. But this is what happens. You have something called the L-adic tape realization, which is an equivalence of categories from MTM. Take it over QL. Before I defined MTM and I was thinking of Q vector spaces. I'm sure it's on, no?
Turn off.
That will be right.
Yeah.
Oh. Changing my battery so I can function again. Okay. Okay. So this is a category equivalent to the category of GQ modules, which are finite dimensional vector spaces over QL. So you have an equivalence of categories, and you have, this gives rise to, so let me make this squiggly thing, meaning gives rise to a homomorphism from GQ to the fundamental group of this category. So before we had a different situation. We had one category included in another, and that gave a surjection of fundamental groups. And here, we have a map from one category to another, which gives a map going the other way. Yeah, honestly, this is really not my specialty, so you're just going to have to believe it. Why does the map go the other way now? I don't know. Because GQ is not to be confused with the Tanakian fundamental group of this category, so it makes sense that this is not the map just between Tanakian fundamental groups of the category. This is, what did you just say?
You go to the Tanakian category, though? As you want.
Well, okay. Take it from me. I'm just telling you what he says. This is really the whole in my understanding. So this comes out of the last chapter of Yves André's book on motives.
Yes, that's okay.
That's what he just said.
Yeah.
Okay, not the same situation as before where we had an inclusion of categories and a surjection. Ah, of course, the fundamental group go the other way. Sorry, I'm going to say it again. Before we had an inclusion of categories and a surjection of groups the other way. Okay. So it makes sense that it goes the other way. I mean, it's not, I don't know anything about surjection or injection. It's just a map. And so it's just a map that we have here. And now we okay, so it is the same map as before. Now we compose the map with that map, which is a surjection. And we call the whole map rho L prime. Now, you notice one thing about what I did before. So I had this filtration that was decreasing, and the successive quotients, and the sum of them, and this was a Dinin-Ihara algebra. And let's just look at the first few of these. So it's always the kernel of a certain map, and the first one is F2 hat, which I'm identifying with pi 1 of P1 minus 3 points, mod itself, okay, the zeroth group. So this first kernel is just the whole of GQ. But we don't use it here. The sum is an I greater than or equal to 1. The second one is mod the commutator subgroup. Oh, but this is all pro-L completion. So the second one is mod the commutator subgroup. And when GQ acts on the abelianization of this, it acts only via the cyclotomic character. And when it acts on an L-adic module, it's only the L part of the cyclotomic character that acts. So this is actually the subgroup of GQ such that the L part of the cyclotomic character is 1. So, in fact, when we use this, we're not using the whole of GQ. It starts at 1. So we're actually only taking the successive quotients of this group. And this group is just GQ mu of L infinity. Okay, if I took the subgroup such that the cyclotomic character is 1, that would be GQ ab. Here it's just the L part of the cyclotomic character is 1, so it's not quite GQ ab. I add only L power roots of unity. Okay, so the Denis-Nihara algebra is really made of this subgroup of the Galois group. So I can just restrict my rho L prime to this thing. And I get a map like this. Now I have a theorem by Goncharov. Again, I'm saying things that I really don't know well, but maybe some of you do. RL is a fully faithful functor. Therefore, our rho L prime has Zariski-dense image and, therefore, the Lie algebras, the associated Lie algebras are equal. Isomorphic, really. It's isomorphic. Yeah, equal, because one is inside the other, so isomorphic. Okay? So the associated Lie algebra of this one is a DIL. The associated Lie algebra of this is what I was calling NMZ dual before. It's the one associated to motivic multiple zeta values. And this, by Brown's theorem, is isomorphic to the free one. Everything always over QL now. These being tensored with QL. Okay, so this is a sketch of the reasoning that makes the final isomorphism that I was talking about this morning. Okay, so I'm going to put that aside now and do something completely different, much more down to earth. So remember we had F GRT, double shuffle, KV. We saw this in detail 2 weeks ago. I wanted to do this not in complete detail, but enough to give you an idea of how it's done. And so that's the next thing I want to do. And after that, I'm going to talk about multiple zeta values and if I have time, the modular forms. Very interesting aspect of all these Lie algebras is that spaces of modular forms are containing them as natural subspaces. So another way in which arithmetic creeps into a situation that looks pretty combinatorial. Okay, so the first part of the proof, so there are 2 parts in this proof. First part is reformulate the defining conditions of KV, a little bit, not too much. And the second is show DS has these properties. So I'll just write down the defining conditions here. So an element, I'm going to call it FG now. An element of KV is a pair FG of Lie elements. So it's in Lie XY squared. XG plus YF equals 0. Before I was calling these A and B. And trace FXX plus GYY equals some constant A trace x to the n plus y to the n minus x plus y to the n. So those are the defining conditions of a KV-Lie algebra. So this one's very, very important. This is what we call a special derivation. So we saw before that Ihara had proved a long time ago that GRT, all the derivations that come from GRT are special derivations. But that wasn't known for DS. In order to prove that for DS, well, the first thing I tried to do was to reformulate what it means to be a special derivation, really to characterize polynomials that give special derivations. So let me just talk about special first, before I talk about the div. So characterize special derivations. So let f be in Lie xy. I really like to characterize f such that there exists a g that makes a special derivation. It's the same thing. If I characterize those f's, then I characterize the pairs. It's not hard to prove, by the way, that if you have an f that gives a special derivation, g is unique. I'm assuming everything is homogeneous of degree n. Like Damien mentioned yesterday, you could change g by plus x. But since I'm working in dimension greater than or equal to in degree greater than or equal to 3, I won't have anything like that. G is really unique. So the theorem says, there's a lot to this theorem, many different characterizations. I'll just give you a couple of them just to be cute. The following are equivalent. F is push invariant. I'll tell you what that means in a moment. Fy, so I always write f as fxx and plus fyy, just grouping the terms ending in x, the terms ending in y. I also write it as xfx plus yfy. It's convenient to write it this way, the term starting in x and the term starting in y. Is anti-palindromic, which just means that fy is equal to minus 1 to the degree, okay, let me assume f is of degree n. Then fy is of degree n minus 1. And this is, anti-palindromic means this, that it's multiplied by minus 1 to a power, which is 1 more than the degree, times the same polynomial written backwards. That is literally, I take each word and I write that word backwards. So that's why I put an arrow here. That's what anti-palindromic means. It's like palindromic, but there's a sign. Push invariant means it's invariant of the push operator. The push operator, it cyclically permutes the powers of x between the y's. So AR, x to the A0, x to the AR minus 1. So it cyclically permutes the powers of x between the y's of each and every word. There exists a unique g such that yf plus xg equals 0. And in fact, g equals s of fx. You can get g back from x, from f. You can get g back from f by the following simple function. For any polynomial or Lie polynomial or whatever, h, s of h is sum for I greater than or equal to 0, minus 1 to the I over I factorial, dx of h, y, x to the I. Where dx is not the dx that Damien used, but a derivation just defined like this on words. So every time I apply dx to a word of h, I diminish the length by 1. and then I put it back over here. So there's a lemma, a very cute lemma, explaining why this S is suddenly appearing here due to Hassinet. Let F be a Lie polynomial. Then F equals S of Fyy. So this is what happens when you project F onto the words ending in Y, and you build F back again by this exact formula. And that sort of explains what... I need to take the Y out, sorry. The Y is get put back here.
Leila? There's just a silly question, but to be sure that I understand well. The bracket you write here, the xg plus yf, is the bracket.
Yeah, that's the ordinary bracket. Yes,
So
that's really just...
the one in there.
No,
Okay.
no, ordinary bracket. You have to think of every element of kv as a derivation. dv of x equals xg, and d of y equals yf. And this is the ordinary bracket. It has nothing to do with the actual bracket of derivations, which is the one that gives you the other thing. Okay, so I mean, there are other equivalent properties, but this is already a cute reformulation. You can see that you have a really simple property on F. In fact, you have two different ones. You can use them, whichever one you prefer.
Are you sure you mean F lower x or possibly F upper x?
I'm not, no, you're right. You're right. Okay. Or S prime of lower F, I guess. It's just the turnaround thing. Okay, so I want to give a little indication of why this works. Firstly, to show that it's actually cute and very easy. No machinery is what I'm trying to say. There's no machinery. You just study the properties of these little functions. So let's see if I can do it without messing up. Lemma. I won't do every equality in every direction. I'll just do a few of them to give you an idea. Suppose xg plus yf equals 0. Then, well, let me even do this. Fy is anti-polynomial. Let me just prove this. It should be very simple. If I don't mess up, it should be very simple. So I write xg minus gx plus yf minus fy equals 0. I have, so this yf minus fy, I'm going to write it as y fxx plus y fyy minus y fyy minus x fxy. Okay, so I expanded the first f as ffx plus fyy, and I expanded the second f the other way with the upper y and the upper x. And I have this. And okay, so there's a lemma hiding inside this lemma, fact. It's not all that easy to prove, but it's a very cute fact, which is a Lie polynomial, P and Lie of xy, can be written xq if and only if P, well, let me write y, it's true for both, but okay, if P has no monomials x dot 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 x, starting and ending in x. No monomials that both start and end in x. Well, one way of this little fact is clear, because if P has a monomial like that, it can't be written this way, because yq minus qy, all the words either start with y or end with y. Okay, and this is actually true both ways. And because, okay, so if I assume that I have this, then yf minus fy can be written xg minus gx. So it can't have any words that start and end in x. Or rather, it can't have any. Okay, I want it with x. So let me put y. It's completely symmetric either way. If it's going to be x bracket something, it can't have words y, y. If it's going to be y bracket something, it can't have words x, x. So in my situation, I know that it is equal to x bracket something. So I know that it can't have words that start and end in y. So these terms which start and end in y have to be 0. So I must have that fy equals fy. If I have a special derivation, it has to satisfy this. But if it satisfies that, well, every Lie polynomial satisfies this. That's a standard fact for all Lie polynomials. So let's see. So let me write fxx plus fyy is equal to minus 1 to the n minus 1 x fx the other way plus y fy the other way. But this is equal to f, and it's also equal to x fx plus y fy. And just comparing the two, what I see is that fy is always equal to minus 1 to the minus 1 to the n minus 1 y fy backwards. This is true for all Lie. I didn't use anything here. This is just a standard property of Lie elements. But in my situation, if I'm special, I have this, which means that this is fy. If f special, I just showed that f upper y is f lower y. So then I get, oops, there's a y too many here. So then I get this. And this means anti-palindromic. This is the definition of fy being anti-palindromic. So what I proved here is, if f is special, then it has no monomial starting and ending in y. So this thing has to be 0. So f lower y has to be equal to f upper y. So just by the standard thing, which is always true for all Lie polynomials, this is a standard thing, always true. But if I have f lower y equals f upper y, then the f upper y is f lower y, and that is antipalindromic. That's what it means. So I did one way of this lemma, and the other way is the same. Actually, everything is equivalent, so you just go back. So that just shows you why. Okay, I'm not going to show you that G has to be exactly that. You can believe it. I'm not going to show you because it's all similar types of details and calculations. Let me instead just show you the equivalence with push invariant. The equivalence with push invariant is important because that's the one that Ikal actually proved. Huh?
Not the result you just wrote.
Oh, sorry. F equals minus 1 to the n minus 1 f backwards.
Okay, yeah, and then you wrote that.
Okay, sorry. But you really don't want to copy all this down, do you? Okay, let me just do this other lemma. What I'm doing here is getting a flavor of the way the whole thing is proved. It's just break it up into a million little steps, each of which is really not complicated. Okay, let's show that fy being anti-palindromic is equivalent to f itself being push invariant. So that's actually really simple. F push invariant means you have every word, the coefficient of a word in x has to be equal to the coefficient in f of the push of that x. xa0. So consider words with AR equals 0. So that means just consider words ending in y. Just consider the words ending in y. What does this say for the words ending in y? It says f Okay, when the word's ending y, it's this. Now here I could just replace f by fy, y, because it's a word ending in y, so it's going to land in this part of f. And I can erase f, I can erase the y, so that's the coefficient of the fy part of this word. And here I could do the exact same thing, except that it's the y fy, and again I can erase the y. So, but this is every word. Now I have every word with less y's, and the coefficient in f lower y is the same as the coefficient in f upper y, so this implies that f lower y equals f upper y, which, as we just saw in the one before, is the same thing as f lower y is antipalindromic. And this is an if and only if to it, goes back the other way, okay? So that shows all these equivalences, these equivalent reformulations of what it means to be special. There were several more of them. They're all very cute. And they just use this type of calculation to prove them. Okay. Now I'm going to talk a little bit about the div and how to formulate that properly in a similar way. So the div property is this. So first let me rewrite this a little bit differently. First of all, I can do this, because the trace of any Lie element is always 0. These are just, it's really easy to prove by induction, and they're just basic facts about Lie elements, like the one I'm writing backwards over there. So since gxx plus gyy is 0, I could just replace the gxx by gyy in the trace. Okay, so I have g equals s prime of f of upper x. So what this means is that gyy is fx of y. When you take the s prime, the only part that ends in y is the thing that you started with, times y. S prime just takes the part ending in y and it adds new parts ending in x, but the original thing is the part ending in y. So gyy is this. So this is just, oh, but I have f lower y equals f upper y. Oh, I'm assuming now that my fg is special. I'm only going to consider the div condition with the special condition. So when I assume that this is special, I have f lower y equals f upper y. So this is just the trace of fy minus fx times y. And this is another reformulation of the div condition. I could write it this way. And this fy minus fx starts playing an important role. And this fy minus fx is very interesting, because f itself is yfy plus xfx. So this, up to a sign, it's basically just like erasing the first character of all the words of f. The reason there's a sign there, I'll tell you why there's a sign. The sign comes from the fact that GRT is included in this natural way that we saw into KV. And you also have this. But the natural inclusion is this one. F of xy maps to this f, which is just f of zy. And here the map is f of xy goes to f of x minus y. And this is where there's a little problem with the sign. In fact, the natural thing to look at is not an f in double shuffle. It's an f in double shuffle. You associate it to an f of x minus y. To put it back to what you hope is GRT, we don't know. It goes back to GRT. But at least it has this form, and that's the one that goes naturally into KV. So if you replace fxy by f minus y, and then cut off the first character, you get this. And this is a very, very particular polynomial that you get from your polynomial. It's a condition like this, which I'll talk about more in a sec. A condition like this is telling you something about the words in fy and something about the words in fx, a relationship between them. And since f is equal to yfy plus xfx, what it's telling you is, all in all, is something about the words with a certain number of y's relating to something about the words with one less y. So the double shuffle relations, the stuffle relations, we saw relations like this. We saw, for instance, that stuffle of 2 and 3 was 2, 3 plus 3, 2 plus 5, and that this is the coefficient of the word xy, x squared y, and here the word x squared y, xy, but the 5 is just the word x to the 4th y. And these stuffle relations typically relate the coefficients of words with more y's and with less y's. When you do the stuffle, you can have relations between words with lots of y's and very few y's. When you do kashiwa ben, all the relations are just with so many y's and one less. So it's like a much more economic system than the stuffle. And yet, conjecturally, maybe they're the same. Okay, so let me finish talking about the div. Once I've reformulated the div this way, let me say what this means. So if I assume that div is true, then actually I'm going to look at it this way, but then I'm even going to ask myself just what this means about f. What is this telling me about f? Can I just have a condition on f that tells me when this is true? So what is the trace? The trace of this polynomial. So the trace is a polynomial, but instead of being in words, it's in equivalence classes of words mod cyclic permutation. So for every word, I'll write C for an equivalence class of that word mod cyclic permutations, and the trace, I can talk about the coefficient of a cyclic class, of a class. And what that coefficient is nothing but the sum of the coefficients of the polynomial in the word for all words in the cyclic permutation class of some given word. So for every word W, I take all its cyclic permutations and I add those coefficients together. And so to say that the trace is equal to something, it's the same as talking about this quantity. So let me just make something clear. When I say cyc permutation of W, I can mean two different things. I can mean the set of cyclic permutations of the word, or I can mean the list of cyclic permutations of the word, including repeats. So here I'm going to use the list. So there may be several copies of the same. It's actually going to be a multiple of the number that it would be if I just used the class. And that's why I have a C here. To say that this is always equal to CA is the same as this. This is equivalence class. And this one, let me write a bar over it, is list. It seems like a lot of work for just a trivial thing, really. Okay, here I have the equivalence class, and here I have the full list, and I multiplied by C over A. It's just a very tiny combinatorial change. N is the length of the word, so N is the length of the list. So when I take the full list, it's bigger, and I have to multiply by this fraction to bring it back to the one above. And now comes something very cute. So I take a word, and I take this list of cyclic permutations. Let me even write it like this. V1, VR. Vx divided by n. Now suppose W ends in y. Suppose I have a word that ends in y. Here, I have a polynomial that ends in y. So actually, I don't really care about all the cyclic permutations of my words, only the ones ending in y. I can actually throw the other ones away. So I'm going to get a bunch of these which will end in y, and then a bunch of other ones which will end in x. And if I just cut the list off and look at only the ones ending in y, which is the only ones that are going to appear here, then u1, ur, is equal to push of u, where this push of u is the thing we saw before. So it's the word itself and all the cyclic permutations of the powers of x between the y's. I am cyclically permuting something, but I'm cyclically permuting something different. I am not cyclically permuting the letters. I'm cyclically permuting the packets of x between the y's. All right, so this is a little lemma. It's really easy to prove if you just take a look at it. I can do an example. So if w is x, xy, xy, say, then this list here of all the cyclic permutations, it's y, x, x, y, x, but I'm not going to pay attention to the ones ending in x. And then x, y, x, x, y, and then some other ones ending in x. But I really only want to keep these two. And w is equal to x, y, x, x, y, x, y. So this is u. And push u is just this word, 2 and 1, and the other word, 1 and 2. So those are just the two words I get here. So I can just replace this by v in push u. Somewhere in this cyclic class is going to be a word ending in y, obviously. So I just take that and I write it uy, and I get push u here. And I can drop the y. So it's fy minus fx u v. Okay? And this is always equal to a constant. It's equal to c. These are all equal. But here I have a c and a c, which I can bar, which I can strike out. So what I now have is that the sum of this polynomial, the one I said was important, over push cycles of words is always a constant. Always a constant for every word. And this is the reformulation of the daisy property. So what it comes out to is, I'm going to put them right here. F push invariant, that means it's special. And fy minus fx, what I call push constant. Meaning when I sum over the pushes of any given word, it's constant. It's always a constant. Except y to the n, which is a special case, but I won't bother with it. This is the reformulation. And from here, you map any such polynomial to kv just by setting the g to be s of fx, and that's your pair, fg. So this is a very nice reformulation to prove that double shuffle works. I'm not going to get into it because it's much more complicated. It's more of the same, but much more complicated. So I'll just say you do have these properties for double shuffle. ds, you have this map. Here's the map how it goes. Here you have an f tilde in ds. You map it to first f, which is equal to f tilde of x minus y. And then you map it to d fg, where f is f of zy and g is s of fx. So this is how you do it. From an element of double shuffle. You have to twist it a bit to do this. And again, I mentioned this earlier. It's a conjecture which is true for GRT. that G equals theta F, where theta exchanges x and y, but nobody knows how to prove that. And in fact, it's also a conjecture that that's true for any pair FT in KV. But it seems really hard. You wouldn't think it would look that hard, would you? But it's really hard.
In KV, it's not with a minus.
Huh?
It's not x and y, and it's with a minus, no?
Well, I actually took the minus away by doing this.
Okay, sorry.
Otherwise it is. Okay, that finishes what I wanted to say about the KV theorem. So now you've seen in detail, pretty much in as much detail as you'll ever need. The GRT goes into double shuffle, and double shuffle goes into KV. Now I'm going to talk about, I'm just doing little, just independent topics, just a few little topics here, things that I think are useful to talk about. So this is just a completely different topic. Generators of GRT double shuffle. Okay, when I use the word generators, I mean element that you're going to need to generate. Conjecturally generate the whole thing, but we don't know. Really, it's some generators. I don't mean all generators. But conjecture, as we saw, this F, the algebra, is isomorphic to GRT, is isomorphic to DS, i.e., GRT, DS are generated by one element in each odd rank, or weight rather, in degree really of the polynomials, n greater than or equal to 3, of depth 1, where the depth means depth equals minimum number of y's in any monomial of f in Lie xy. So to be of depth 1 exactly means that the coefficient of the Lie word, add x to the n minus 1 y, or just of the word x to the n minus 1 y is not 0. This is the only Lie word of depth 1. So if you have a Lie element of depth 1, it has to have this Lie word in it. So it has to, in particular, have this monomial in it. Okay?
What supports this conjecture? What supports this conjecture?
What supports this conjecture? Okay. Apart from calculation,
Why should it be equal?
okay. I'll tell you, there's two different answers, one concerning GRT and one concerning DS. So if I was going to say, why should DS be equal to, why should it be equal to F? Why should it be generated by, why should it be equal to F? Well, that will lead me into something I was going to talk about. I'm about to talk about it, but in a word, to say that F, which injects into DS, is isomorphic, to say this, it means that this surjection we had before, but I'm going to come back to it, is isomorphic, which means that the only algebraic relations between multizetas are double shuffle. And for some reason, this is widely believed. So why is it widely believed? It would mean that there aren't any others between motivic multizetas either. So you can wonder, why is this widely believed? And the first thing you'd like to say is, well, there are many algebraic relations known, and when people study them, they usually manage to get them from these double shuffle relations. And that would be great, and it's true to a large extent. But it's not completely true, because the associated relations well, which way does that go? Now, we have GRT into DS. So this surjects. Well, I need some kind of a language here for the dual of UGRT, associator relations. this surjects. That means that everything that satisfies an associator satisfies double shuffle, but we don't know the contrary. We do not know whether everything that satisfies double shuffle relations also satisfies associator relations. So you can ask yourself legitimately, why would anyone conjecture that these are the only algebraic relations? Yeah, where does the conjecture really come from? A desire? But that is the motivation between the idea that they could be, and this would be the same. One way of saying it would be that the associator relations express all algebraic relations between multiple zeta values.
Is this first ISO conjecture analogous to the fact that we hope that the Galois group is isomorphic to GT or not? Or I'm making a big mistake?
Well, actually, this is much, much weaker than that.
Okay.
Okay, on the Lie algebra level, we certainly do hope that, and that's equivalent to the Deligny-Haar algebra being isomorphic to this. And now we know that these two are isomorphic. So, but even if this were proved, that's much weaker, obviously, than the other thing. But yeah, it's the Lie algebra analog of that question. Sure, that's one way of seeing it, now that we know this isomorphism. But there's also just the idea that F is the fundamental Lie group of mixed Tate motives, and that what you're saying is that you can master the mixed Tate motives. You can completely understand them, that there are no other algebraic relations except associator relations. That this whole category is completely described by associator relations. Okay. So now I'm going to tell you, I told you before how Drinfeld originally just came up with an element in each odd way, an element like this, one element in each odd way, to show that there exists one. And I showed you a method where you could choose a basis of multi-zetas, but it wasn't very canonical. So now I'm going to show you a different method. So I like this because I'm going to put everything together in one huge picture. So here, I'm going to take polynomials in these two variables. Here, I'm going to take u of ds, u of GRT, ds, GRT, and I'm going to put all these arrows. So these get included. Like this. And it's really just literally inclusion of polynomials. They're all polynomials in x and y. They're all just polynomials in x and y sitting inside each other. Here, there's fxy goes to fx minus y. So this isn't quite a literal inclusion of polynomials, but it's so close that I'll pretend that it is. Now I have a duality here. Duality. I want to look at the dual picture. So what is the dual of this? The multiplication here is just a basic concatenation of words. And for every word, for every monomial over here, I'm going to have a dual symbol. I'm going to call it like this with a bar over it. It's purely a symbol. To every word, I have this, and it acts on that word by 1 and all other words by 0, and that's all it is, a dual basis to the words. And now I'm going to dualize the entire diagram of inclusions there to surjections. So here I have what I call formal zetas. So what this is it's an algebra of symbols that look just like zetas, zeta of k1, kr, but you know they satisfy only double shuffle. You decree they are subject only to double shuffle, nothing else. So I'm just going to quotient out by double shuffle relations without going into details of what I mean by double shuffle and regularized double shuffle. Just there's a set of double shuffle relations that I quotient right to get this. And this goes down to a formal GRT. I don't have a notation for this one, but it's the dual of that. Now, the dual of an inclusion of a Lie algebra into its enveloping algebra is mod products. Mod products in the degree 0 part, constants. So I'll call it NF GRT. NF is Z. All surjections. Okay? Now, the interesting thing about this diagram is that it's explicit up here. There's an explicit map from this object to its dual. I just map a word to Z of that word. And which you don't usually have, right? Usually if you have a dual vector space, you don't actually have a map that's canonical in any way. But here you do. And it goes all the way down. This map, it just goes all the way down. You get explicit isomorphisms between the dual objects on every level of this. And this one, okay? And oh, and there's one that I've forgotten. Our friend motivic zetas. Both of these surject to the motivic zetas. Because it's known that motivic zetas, which I'm not going to define, but which you'll hear a lot about next month, but you can think of them for now as just being an unknown quotient of these, of symbols satisfying these relations and those relations and maybe others, but that have the property that its structure is completely known. It's a free. It's a freely algebra on S3, S5, S7, and so forth, what we were saying. And this one goes down to there. And so here, we have an NMZ dual injecting into here. So this is the freely algebra by Brown's theorem. This one's the one that's equal to S. Okay, but we have a little more than just having all these beautiful inclusions and their dual surjections. We actually have explicit isomorphisms between every object at every stage of this diagram. Literally, I can take any element of this, I take a basis of this, write an element in the basis with unknown coefficients, just an arbitrary linear combination of the basis. So with unknowns as coefficients, just consider it as a polynomial here. Just write z in front of every word, formally. Quotient by the relations. Come down to wherever it is. If I start here, for instance, I'll come down here. And suppose I want to find the correspondence to a given zeta, like zeta of n. Well, I come down here and I write it in any basis of this. It doesn't matter what basis I choose to do this calculation. I just write it down in a basis and I solve for zeta of n. And then I find the exact, precise, explicit polynomial over here, which is the dual of zeta of n. Okay? And as far as I'm concerned, well, zeta of n corresponds to the word zeta of x to the n minus 1y. So this is always going to give me a depth 1 polynomial over here. And I'm talking about odd n's greater than or equal to 3. Obviously, zeta 1 is 0. And zeta 2, I'm not considering it quotient alpha yet. I don't want even ones. I only want odd ones. So every zeta n for odd n greater than or equal to 3 gives me an exact, precise polynomial over here that I can actually calculate. And over here as well. Also here you have a motivic zeta of n. And here too you have a precise counterpart. But the trouble is that you can't make the calculation I just said. Because if you take here, you know the structure of this, you know it's free. So you take a linear combination of the basis, you go up here, you dualize, you come down, but once you get here, you do not know what to quotient by, because we don't know. It's the same as this. This quotient here, we don't know what it is. We don't know what other relations are satisfied by these. So you cannot do the calculation that I'm saying explicitly on the motivic level, just because we don't know what this quotient is. But for all the levels above the motivic level, you can do it explicitly, and you can write down both for GRT and for DS a polynomial in every odd weight greater than or equal to 3. That's the dual in its explicit sense, I just said, of zeta of n. So as far as I'm concerned, that's a very nice canonical set of generators. It would be even more canonical if I could get the one down here and know which elements of GRT they are. But that one, you can't do it explicitly. However, if you believe that they're same, which I of course do, then what I'm doing is going to give you the canonical generators, okay?
The rows in the middle, it just means that there is a duality between the two spaces?
It's an explicit isomorphism is what it is. Of a vector space and its dual. So whenever you have a vector space and its dual, you don't have a canonical isomorphism, but here you do. Here you do because you have that here, because nothing could be more canonical than a word and the symbol of that word.
If you compose the 3 rows,
yeah, the whole thing commutes everywhere. This completely explicit morphism from a vector space to its dual passes down through the whole diagram and gives you explicit canonical.
Does this mean that you can build a map between DS and GRT? if you go from ds to nfz,
Yeah?
and then you go down, and then you go back by the reverse isometric.
Well, then you get this map, which you already know. This map is f of xy maps to f of x minus y. Yeah, if you do what you just said, this is what you get.
No, the other way around, but it won't be a map of Lie algebras. That's the point.
But of vector spaces.
Of vector spaces.
But so this means that this gives some information about the dimension of the spaces.
Yeah.
But there are
It
infinite
seems that you have a
dimensional
map the other way around then.
Hmm?
You have a map from DS to GRT, just of vector spaces.
Yes.
It just means that you have a splitting
And
of
it
your
is
injection.
subject-
Yes, it's a splitting. You haven't, that's true. See, that's very strange. This situation comes up in much more general with roots of unity in your multi-zeta values and all kinds of general facts where, yes, because of this diagram, you also get maps going always the other way, which are splittings. That's exactly what they are. But I mean, that would be great if they were isomorphisms, I wish, but all you get is splittings for the moment. But even that's very strange. I've tried to make sense of that, but it's not very clear. Yeah, it does mean there are natural maps going the other way, but they're not Lie algebra maps. This is only vector spaces. Everything here is really only just vector space maps.
By the way, Leila, I have one question. I just forgot. What's the difference between capital MZ and NMZ?
A product, mod products. All of these N, it's new. It's the new generators of these rings, which means not counting products of smaller way
Oh,
generators.
sorry. Yeah.
So I go mod products, and what I get left is a set of ring generators forming a vector space. So finding a canonical set of depth 1 elements which are conjecturally generators, but even without being generators, they're a canonical set of depth 1 elements in each odd rank was a question that was asked by people for a long time, and there have been many different answers to it. In fact, there have been so many different answers. Ecal also has a completely different method for finding these. There have been so many different answers that I think the word canonical doesn't apply. So I stopped using it. Zeta FN is about as canonical as something it can be, but when you actually calculate these generators, they don't turn out to be really nice in any number theoretic sense, like having nice denominators. So still, they're the duals of zeta n. So there's really enough to work with. And there's lots of things you can do with this game explicitly, like many people, like Broadhurst, Kreimer, and even people who are working with Francis Brown's theorem that gives an explicit basis for MZ, they want to decompose any given multi-zeta value in terms of a given basis. And the only way they have to do this, first of all, you have to find a basis of multi-zeta values. And if you're working with real numbers, you have to use a computer program and write your numbers with many, many digits after the decimal point and try very large rational coefficients with lots of numbers and try to make your decomposition. Whereas this diagram actually spares you from doing all of that. Because if you have a basis here, okay, first of all, if you have a candidate basis, you can just check it's a basis. Because you just dualize everything and check it's a basis of polynomials for a polynomial space over Q. You see if they're linearly independent. So the first thing is to a candidate basis here, instead of checking with real numbers, you just check it with polynomials over Q. And then when you want to decompose any given multi-zeta into a basis, well, you're just decomposing a polynomial over Q into a polynomial basis over Q. So it completely spares you the need to study these things with real numbers and thousands of digits after the decimal. So that's one of the uses of this system. Oops. Okay, let's see. That's finished that topic. Okay, I want to talk a little bit about another topic. I want to talk about period polynomials. This is another thing that's very nice. That appears, it's number theory appearing in these Lie algebras. So definition. The depth, which is exactly what I defined before. It's gone now, but it was the minimal number of y's in any monomial, gives a filtration on well, they should all be the same, so I wouldn't have to write all this, okay? You might think it would be a grading, but it isn't a grading for several reasons. One of the reasons is that, quite simply, there's no element of any of these the algebras which is in the given homogeneous depth. Never. Even the very first element, it's x, xy plus xy, y. So here you've got depth 1, and here you've got depth 2. There's actually no element in a given homogeneous depth in any of these. But there's another reason for which it's not a grading. You could still say, well, take the depth 1 elements. Those are the elements that have a non-trivial coefficient of x to the n minus 1y. And the depth 2 elements and so forth. And now I'm going to show you why that is not a grading. Not grading. Because there are relations. And I'm going to give you the very first one of those relations. So, first of all, dim GRT equals 1 in weights 3, 5, 7, and 9. So for small values of odd n, there's just one element, the one element of depth 1 in odd rank that we can calculate explicitly. That's a scalar multiple. Also for ds and kv, obviously, if we saw any difference between the algebras, we wouldn't conjecture they were isomorphic. Now you take the Poisson bracket of f3 and f9 minus 3 times the Poisson bracket of f5 and f7. And so it's just a polynomial. It's just a polynomial in x and y. It has a very interesting property. These are of depth 1. They have monomials with 1y. So the Poisson brackets are of depth 2. So they have monomials with 2y's, and this one has monomials with 2y's. But they all cancel out. In fact, this one is in depth 4. All the terms of depth 2 cancel out. All the terms of depth 3 also disappear. And the remaining terms are of depth 4 and greater. So what that means is that in the associated graded, you have a relation. So this is a relation in GRT 2 mod GRT 3, or 4 even. So we are conjecturing that the algebra is free with one generator in each odd rank, but the depth filtration is not free. The associated graded is not free. So there's two very, very amazing things about this polynomial. One of them is these coefficients, 1 and minus 3. That has deep number theoretic content, which I'll tell you about. And the other, which is even more mysterious and surprising, is that when you calculate this polynomial, I've normalized all of the fn's, so the coefficient of x to the n minus 1y is just 1. So I've just taken that scalar multiple. You calculate this polynomial, and you write down a big polynomial over here, and what you get is 691 times a polynomial. But there's some denominator which I don't remember, 144 maybe, times a polynomial over z. Okay, so this is a Bernoulli number. This is the denominator, the numerator of B12. So here you have a Bernoulli number appearing in GRT, which is defined by a pentagon. This is very striking, or defined by double shuffle, or defined by the KB relations. This relation is there. It's there in all of them. The 691. Obviously, this relation is true in GRT, then it's true in the other two because they're included in each other. So 691, it appears everywhere. And yet you never think to see a Bernoulli number from that definition, would you? Although Bernoulli numbers can give surprises by popping up in all kinds of places. So in fact, you have an explanation for this identity. It's a general phenomenon. You really would like to know, say, when you have linear combinations like this, for I plus j of some fixed weight, which there is 12, which are of depth much greater than they should be. So showing that your depth filtration is really a filtration, it's really not a grading, it's really not as nice as you would like it to be. And the answer is, that works if and only if, so you take that thing and you make a polynomial out of it by doing this. Is the period polynomial of a modular form of weight n on SL2 of z. So let me say a modular form of g, I'll call it g. The period polynomial is given by integrating your modular form against z minus x term, which gives you a polynomial in x after you finished integrating. Okay, so what this gives you is natural injections let En equal, okay. Let's say the map modular form to period polynomial defined this way gives you a map from Sn of SL2 of z to a space of polynomials, a vector space of polynomials En. The dimension of this is well known. N minus 4 over 4 minus n minus 2 over 6. And now what this gives us is an injection from this into GRTn for all even n. There are no modular forms for n less than 12. So you have something one-dimensional for n equals 12. There is a delta for 14, and then after that you have bigger and bigger spaces of modular forms. Okay, so inside GRT we discover spaces of modular forms. Now you can wonder if there are any other weird relations like this in GRT. I say GRT, but I'm always equivalently speaking of DS or KV. Same questions for all of them. Are there any other strange relations like this, where linear combinations of things at a certain weight and then they land in a higher weight? Of course, you can take a relation like this and bracket it with anything and get a relation. But are there any others, other than the ideal generated rates? Are there any others?
So this theorem G is cusp form, no?
Cusp form.
Even period polynomial.
Okay, reduced. Let me just, okay. You have to take a cusp form, and what I wrote over there is action space of cusp forms with dimension of cusp forms. And here you have to say reduced even. And what that means is, quite simply, you take this polynomial, you take even part, you just forget the odd part, you just take the even part, so you take it plus itself minus x over 2, and remove term of height of degree n minus 2 and constant term. This is the reduced. So you take your period polynomial, you take the even part, you remove this. But you still have the map that I wrote up there. Even if I replace period polynomial with reduced even period polynomial, it's still an isomorphism. So let me show you the Broadhurst-Kramer conjecture. Broadhurst and Kramer gave a function, a generating function, so O of over 1 minus x squared. When you take the Taylor series of this, you get one generator in every odd degree. So it's like a generating function for the generators, the conjecture generators of the Lie algebra. And f of x is x12 over 1 minus x to the fourth, 1 minus x to 6. And this is a generating function for the dimensions of the spaces of cusp forms. It's exactly those numbers that are given there. So, conjecture. This is not exactly what they said, but they said it for multiple zeta values, mod zeta 2, and I'm going to say it for GRT, but since there are conjectures linking all of these things, it's sort of equivalent by conjecture. Let me write BK. BK is generating series for dimensions of U, GRT, or double shuffle, whatever, in depth D, weight n, over U, GRT, in depth D plus 1, weight n. So, in other words, this dimension would be the coefficient in BK of the monomial x to the n, y to the d. So what they did when they actually came up with this function is, firstly they came up with a slightly modified function, which I can never remember. Maybe there's a y squared here or something. They did what I was saying before. They took multiple zeta values as real numbers, and they tried to calculate the dimensions of the weight n spaces. Mod zeta 2. This function describes mod zeta 2. Otherwise, you modify it a little bit to get the full thing. And they found these numbers, all those numbers, bunch of numbers, huge bunch of numbers, and they tried to figure out what generating function this was, and they kind of came up with this function. Okay? Now, as far as we've been able to calculate with all our isomorphic-looking Lie algebras, these are the right dimensions. And what does this mean? If this really is the generating function, what does it mean? It exactly means that if I let y equals 1, first of all, if I let y equals 1, this goes away, and I just get this. I get 1 over 1 minus O of x. And that's the generating function, ignoring the depth filtration, just completely ignoring the depth, just for the weight n parts of the associated gradient. What y is doing, this y here, y is telling me the dimension of the depth d part of the weight n part. And this is very particular. What it's saying, I did the signs wrong. It's minuses and pluses. What it's saying is, you take the thing of weight n and depth d. And inside it, you've got a bunch of things which are no longer of depth d, but something bigger. And you have exactly the dimension of s of x of those things that go away. And then you put them back in depth 4. And that's exactly what we saw with that one relation. So here, we had f3, f9, minus 3, f5, f7. Went away in depth 2. It should be in depth 2, but it goes away. And that, the corresponding polynomial, it's the period polynomial of the Ramanujan delta cusp form in weight 12. And I told you that this is in depth 4. It looks like it should lie in depth 2, but it lies in depth 4. The dimension for n equals 12 is 1. So the coefficient is 1. It looks like the depth 2 part should be of dimension 2. If you just ignore that and you just look here, you would get a coefficient of 2. But in fact, you have to subtract off the 1 of this relation and put it back in depth 4. So what this conjecture is telling us is that nothing else happens except these relations. The relations I just told you completely explain this term, and the fact that they conjecture that this is the generating series is the same as conjecturing that there aren't any more other weird relations that happen, nothing but this. On the other hand, they don't really believe in their own conjecture. I mean, Broadhurst was saying to me, who knows, this might be true, but in weight 300, there could be other relations. We really don't know. It's not like we have any evidence for this conjecture whatsoever other than numerical. There isn't any theoretical evidence for this one. Still, it looks good though. And the structural explanation of it is that you have these spaces of modular forms inside these Lie algebras that do a very strange thing with the depth filtration. But you don't have anything else strange going on. For the rest of there are no other relations in this.
The signs were right before.
What?
The signs were correct before.
Oh God, you're right. Take away this. Okay, what I really want to do is this. There. This is how I want it. Okay, now, take this, subtract off depth 2, put it back in depth 4. Oh, and another thing that this prediction says is that these period polynomial elements here are always in depth 4, which we don't know. This one is, certainly, you can just calculate it, it's in depth 4. Whenever we calculate them, they're always in depth 4. But it's hard to see if they're not actually in depth 5 or 6. I mean, theoretically speaking, they might be in higher depths. But what this structural generating series is telling us is that they should always be exactly in depth 4. Something else that we aren't able to prove. Okay, I don't know if I have any more. Let's see. Oh, yes, one last thing. Let me talk a little bit about the very last thing. So all of this is stuff that's going on in the subject, really. Just different aspects of things that people are looking at and trying to prove. And the very last one I'll mention briefly is something very, very beautiful, which is elliptic GRT. So there are two separate pieces of work on this subject. So let me give you first some work done by Hain and Matsumoto and Pollack. What they were trying to do was, they were trying to study motives, mixed-tape motives, just very much like what we were briefly looking at before over Z, but they wanted to study mixed-tape motives over an elliptic curve. They wanted to define a category of mixed-tape motives that's bigger than the one that we saw before, with a genus 1 component in it. So they actually defined this. So category of elliptic mixed-tape motives, and they were able to compute the fundamental Lie algebra. And the fundamental Lie algebra of this is, something to keep in mind is that you have a GQ action, a GQ and also a GT action, on SL2 of Z hat. Because this group, it's the pi1 of the fundamental domain of elliptic curves. It's the pi1 of the moduli space of elliptic curves. And just as we were seeing the GT and GQ act on all pi1s of moduli spaces, in particular it acts on this one. From this action, they obtained the structure of the fundamental Lie algebra as F, which you have to remember is the fundamental Lie algebra of just NTM, acting on, so a semi-direct action, on a Lie algebra constructed from using all representations of SL2 of Z. Lie epsilon 2I, I greater than or equal to 0. Now the way to see this is, these are derivations of Lie of xy in the way we saw before. And these are derivations of Lie of xy in the way I'm about to define. And the whole thing, again, the whole big thing, lives inside derivation of Lie of xy. So I'm just going to tell you who the epsilon i's are, and then I'll quickly tell you what Enriquez has done in this direction. I think that will be plenty.
Even in their special?
What?
Do they lie in their special? Or only in their? You make the point.
They don't lie in their special. The F part does, but these don't, as you'll see right away, because I didn't tell you what they are. And unfortunately, they don't. I really wish they did. That makes them much harder to work with. So this is epsilon 0. It's a bit special. And all the others are defined by this formula. Oh, let me write it this way. Minus xy, well, okay, add xy, add x, 2y minus 2y, plus the next term all the way to the end. So you just keep moving it x to the left. So this is depth 1. This one is depth 2. Okay. Now, they have a lot of conjectures about the structure of this, but no results, only conjectures. The conjecture is, okay, we do have one result. We know that this is free. No relations here. So to describe the relations of this Lie algebra, you need to know all the relations in here, and then you need to know the action. So they have some nice conjectures on both of these things. And in particular, they have a complete set of conjectures about all the relations here. And the relations between these things are very closely related to the period polynomials I was just talking about. For instance, epsilon 4, epsilon 10, minus 3, epsilon 6, epsilon 8 equals 0. It's like what happens with F3, F9, minus 3, F5, F7 in the associated graded. So this is actually much simpler because these are homogeneous in depth, whereas elements of DS are not. So these are actually simpler to work with. Nevertheless, they have many period polynomial relations between the epsilon 2i, which they write out explicitly what they believe all these relations to be, but this seems really quite difficult to prove. And then they have also some conjectures about the form of the action of f on these, but everything is very conjectural and not very explicit when it has to do with f. So they wrote a paper which they never published because it's too full of conjectures and no proofs, but basically detailing what they believe the structure of this looks like. And quite separately, independently, Enriquez tried to study the action of, he did a very remarkable thing. He tried to study the action of GT on genus 1 mapping class groups. Now, we saw in Pierre's talk last week that actually we needed to add another relation in order to get GT to act on genus 1 mapping class groups. But he didn't look at the full mapping class group. He looked at the braid group inside the mapping class group. So the braid group on a torus, you have to imagine a torus, you have mark points on your torus, and you let the mark points move around the torus. Just like we let the marked points move around a sphere to get the usual braid group. Now they move around the torus, and that forms a subgroup of the mapping class group. It's called genus 1 braids. I mean, you can do it for any genus G braids. Okay? And what he found is that contrary to, personally, my expectation, GT acts, for instance, on B13, and I think maybe he even proved in his head, not in his paper. Maybe he even just is aware that this extends to B1n for all n, which is a highly non-genus 0 situation. I mean, this is really higher genus situation. So I must say I was extremely surprised by this result. I just thought GT will not go into higher genus, and suddenly it did. So from doing this, he then tried to get a Lie algebra analog on braid group, one of these braid Lie algebras that I think Damien was talking about yesterday, which I won't go into in detail, but his theorem says, it's a theorem definition. He defines a new Lie algebra that he calls GRTL. And he defines it as, he defines it explicitly by saying it's all things having such and such properties that are really complicated, but just come from the fact that it is a derivation algebra of this braid algebra, so they're just relations that you write down. But then he proves, and this is interesting, he proves that it's a semi-direct product of the normal GRT with RL. And he proves that RL contains these Lie epsilon 2i's, which he didn't get from Hein and Matsumoto's work, but come separately from what he was doing. He came up with the same things. And he conjectures that these two are equal. So we have a conjecture that F is the same as GRT. We have a conjecture that the Lie epsilon 2i's is the same as RL. And Therefore, we can now make a conjecture that what he's doing is the same as what they are doing. But there's a big difference in what he's doing, is that everything's completely explicit. You may not be able to calculate RL and determine if it's this, but what you can do is take an explicit element of GRT and explicitly calculate the explicit action on this explicit derivation. So then you know exactly what the action is, and you can verify some of the conjectures that they made in this situation. So this is something that's really, really recent, actually, and unpublished, actually, at this point. And it's what I'm working on now. This, very interesting. This and the period polynomial relations between the epsilon 2i's, all of this nest of conjectures made by Hein and Matsumoto around their elliptic situation.
Thank you.
Enough dim sum.
Do we have quick questions?
There seems to be a shift from 3.9 to 4.10, so a shift by 1.
Yeah, I'll tell you why. That's really simple. I wish everything was this simple. Epsilon 4 of x is add x to the fourth of y, and epsilon 4 of xy, let me call this a. I'm going to call this a and ab. I'm just going to change letters. And I'm going to include Li of xy into Li of ab this way. This is typically what happens when you take a torus with a point and you make a cut here and you get something of genus 0 and you include the pi 1. And it's just like this. And this is 0, which you can explicitly calculate with ease. And this is a, let's see. This is add x to the third y, right? Because I just pushed AB over to become y. So now I can translate E4 as being E4 of x is x squared y. Well, add x squared y. And E4 of y is 0. Usually when we do a GRT, we have it the other way. We have E4 of x is 0 and y is y bracket. But okay, it's very similar. And this is just at the beginning of F3, x squared y. And then F3 has other terms, okay? So E4 acts the same as F3 for this reason. And all of them do it. And that's, in fact, that's how you can easily deduce that relation from the one that we have. But the difference is that they have many, many more relations, which we can't deduce so easily from the ones that we have. So yeah, this one and all the similar ones like it come directly from the ones that I said before. But then they have so many more. This is important. In fact, it's a little bit of a cheat to write xy all the time, because it's not really the same xy. It's really connected with the usual xy this way, and it really is a genus 1 situation.
So this elliptic, you wrote elliptic GRT is a semi-direct product of GRT and RL. And the RL contains this real algebra which, so this sub-real algebra is stable by the GRT.
We don't know. I know. That's one of the conjectures. I wish. If it were, it wouldn't so much matter whether they were equal, because we could just throw away the extra. But no, I don't know how to prove that.
So,
Yeah.
Shall we resume?
I'm
always interested in the AI. Shall we say in 30 minutes?
I don't have anything else to say.
Ah.
I'm dry. So unless you have questions, I think it can be
Sure. So do people have long questions and stuff like that? For people who are interested, you come in 30 minutes and you see. Yesterday for Damien, we were 4. So after 2 minutes, we said, right.
Yeah. I mean, I can talk more about multi-zeta values, which I didn't talk about or not. But I don't have anything else planned.
Okay.